Lecture 8, Probability and Counting Rules. Learning objectives. In this lesson, you will learn sample spaces and finding the probability of an event using classical probability and empirical probability, and learn the probability of compound events. Now, we have some basic terminology. First, let's start with the probability experiment. It's a chance process that leads to well-defined results called outcomes. So, for example, you can say rolling a dice. Then an outcome is the result of a single trial of a probability experiment. Single trial means like you do it only once. So you roll it once, you roll a die once, and the outcome, for example, here, outcome can be something like 1. For example, you can roll 1. It's an outcome. Now, the sample space is a set of all possible outcomes of a probability experiment, and it's denoted by S. So here you can say all outcomes are 1, 2, 3, 4, 5, 6. And then an event is a set of outcomes of a probability experiment, is a subset of, let's say, or set of outcomes. Yes, for example, an event is something like a subset. So, for example, getting 1 or 2, it's an event. And the probability is the chance of a specific event to occur. Okay, we will learn about this. This is a mathematical value. It gives you the chance that the event occurs. Now, examples of experiments and outcomes and sample spaces, and these are the most common ones, especially the first 3. Tossing a coin once, the experiment is this, and the outcomes are head or tail, and the sample space is the head, tail, and rolling a dice once, you get the outcomes 1 up to 6, and then you can write the sample space as the set of 1, 2, 3, 4, 5, 6. And if you toss a coin twice, then you can, the first toss, H, the head, then the second head. So we have 4 different outcomes. So this is for the first one, first toss, and this is the second toss, the second letter here. And this is the sample space. When you play a lottery, the outcomes you win or lose. And then you write the sample space as win, lose. And if you take a test, and let's say it's a pass-fail test. It's a pass-fail test. So you have 2 results. You passed or failed, so you have 2 outcomes. And the outcomes can be 2, 4, any number, depending on the experiment you do. And also you can, if you select a worker, you can say the outcomes are like being female or male, or in a question you can say it's true or false. And depending on the experiment, you can have different outcomes and different number of outcomes. Now find a sample space for rolling 2 dice. Okay, so you have 2 dice. You have 2 dice. You have here. Okay, and you have another one. Another one. Okay, you're rolling them, and then how many outcomes do you have? So you have 1. You can have here 1. You can have here 1. You can have 1, 2, 3. So this is a way of counting all the possibilities. Then you start with 2. Then you can have 1, 2, 2. and then you will have 6 numbers here, and for each number you have 6 possibilities. So in total you will have 36 cases, or 36 possibilities. Now you write all of them. Okay, so you can write them this way: 1 1 1 2 1 3, and it will make 36. So it makes a sample space for this experiment. Okay, let's look at another example. So find a sample space for the gender of 3 children in a family. Now, there are 2 genders. We know it's male and female, or we can say boy or girl. Hence, there are 8 possibilities. We will see now. Now, we can, so we have to count them. Let's say first child, the second child, and the third child. So let's put all the possibilities, so we can have like boy, 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 girl, boy, boy, girl. Okay, let's do boy, girl, and then we can have like a girl, boy, girl, girl. Then we can have the girls here, girl, and then boy, boy. So we can repeat these 4 again. So we can have the same thing here, G, 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 and so in total, we will write that the first possibility is all boys. The second one is the B, B, G. The third one is B, G, B, and then the other one is B, G, G. We have more here. And then when you list all of them, then you will get the sample space. Then you will have this sample space. So in total, we will have 8 elements here: 1, 2, 3, 4, 5, 6, 7, 8. And each of them is an outcome here. And how can we count it easily? So we can use tree diagrams. So, you know, in the question, it was not easy to list all of the possibilities. So it's a tree diagram is something like this. You know, it emanates. There's a starting point, and we have the branches emanating from the starting point. Then the line segments, we have more. So it goes like this. You know, it might be 3, 4, anyway, 2. So this is a tree diagram here. This is a tree diagram. So what you understand is this one. Now we can use the tree diagrams for counting purposes. Now let's do it. Let's do the previous question using the tree diagram. So this is how it goes. The first child, you can say here, in the first child, you will say B, and then you can write here G. We have 2 possibilities. Then for B, we have 2 possibilities for the second child, BG, and for after the second child, we have 2 possibilities for the third child. So here, each branch here, each separate branch gives you 1 possibility. So we might have BBB, then BBG, then BGG, and BGB. Each of them is giving a possibility. So this is if you put them in the space in the set, so you will get the sample space. Okay, the number of outcomes in the sample space, and we have some other type of problem here. We'll see an example. How many outcomes in the sample space of tossing a coin 5 times? So here, when you toss a coin, 1 time you get head or tail. 1 toss gives you head or tail. But when you make 2 tosses here, it will be the first one. So you have to think the first toss, the second toss. What can it be? What can the first be, and what can be the second be? And yeah, it gives like 4 options here, 4 situations. The question here is how to get 5 tosses. And the listing might be a little hard to do because you have this H, 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 the first toss, second toss, third toss, fourth toss, fifth toss, and then it goes like H, 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 H. The last one is T. So it will take some time to do all these. So instead of this one, we can use a formula here. The formula is, it's a rule. So this rule is saying the number of outcomes in an experiment of n trials, where each trial has k outcomes is kn. So I can formulate this one this way. If one trial has k outcomes, then if we repeat it n times, then we will have k to the nth outcomes. You can keep this in your mind. One toss, 2 outcomes, and n tosses, 2 to the n outcomes. So you can, so if you apply it to our question here, 1 toss, 2 outcomes, and 5 tosses, it will be 2 to the 5th outcomes. So it gives you just the number of the elements here. Okay, now let's look at this exercise. So a Saudi Arabia football team must play 2 matches. So how many points are there in its sample space? And it says write the sample space if the team must play 3 matches. Now let's count all the possibilities here to get all the possible points. So in the first match, we will look at the results in the first match and the second match. And by the way, if you don't know football, there are 3 results in football. There is win, one team wins or lose, and then draw. Draw means they have the same goals, number of goals, or 0-0 or 1-1, 2-2. So win makes 3 points, and loss makes 0 points, and the draw brings 1 point. Now, by using these points, we will try to get all the possible points from 2 matches. Now, let's do the tree diagram. So we have 3 matches here. I mean, 3 results for the first match, so it might be a win, and then loss or draw. And then the second match also have 3 outcomes. Now, let's look at them. So WW team wins both matches, so it will be 3 plus 3, 6 points. And WL, so it makes 3 plus 0, which is 3. And WD makes 3 plus 1, it makes 4 points. And in the same way, we can say this is 3 points, and this is 0 point, and this is a 1 point, and here are 3 points, here 1 point, and here 2 points. So when you look at all these, the sample space for the points has to be 0, 1, 2, 3, 4, and 6. So this is the sample space for all the points after 2 matches. Now let's have a detailed look at event. Now, an event is a subset of the sample space. We know it. Now, an event is a subset of sample space mathematically, but generally an event is stated in words and problems. So let's have a look. So consider the sample space of the outcomes of a rolling dice. So here 1, 2, 3, 4, 5, 6. This is the sample space here. Now, for example, take a subset. So when we take a subset, it's just some elements from the set, so it makes a subset. So you can write it this way, but in the problems we say this is the event of rolling a number less than 3. So this is rolling a number less than 3. It's 1, 2. In the questions, you can see it this way, like what's the probability that we roll a number less than 3? Or what's the probability of the event of rolling a number less than 3? So for 2, a singleton set with one element, which is 2, we can say this is the event of rolling 2. And another subset, it can be given as rolling a number between 1 and 6. So in this case, you have to think, okay, this is 2, 3, 4, 5. And okay, let's empty set. So in some cases, we might have an empty set. There's no element. So for example, what is it? We can say this is event of rolling a number bigger than 6. So it's not possible. So you cannot have anything bigger than 6. So this is, then we write it as empty set. So these are important because in the problems, we give you the statements, not the sets clearly. Now let's have a look at here. We know an event is a subset of S, so then events may be classified into 4 types. One of them is simple event, so it means it has only one outcome, so one element within the subset. And a compound event is an event with more than one outcomes. And certain event is an event that contains all outcomes, which is equal to the sample space. A null event is an event that contains no outcome, so it's impossible, or we say it's empty event or empty set. So mathematically, all events are corresponding to sets, subsets. So when we say an event, so you have to find the corresponding set in order to calculate the probability. Now let's look at this example. And in this example, we know the sample space for the gender of 3 children. It's already given to us, and already we found it. So the sample space for the gender of 3 children in a family, it's given here. So we already found it. And it says write the corresponding set for each event and determine the type of the event. Now let's see. Now A, all children are boys. So this is the event. So which set is it? It will be all boys. Here, let's check for it. So it will be just boy, boy, boy. And which type of event is it? So it has only one element. So A is corresponding to the singleton set, and this set is okay. It has one element, so it's simple event. Now B is the event that there's only exactly two children of the 3 girls are girls. So it's there. Okay, let's say exactly 2 girls. So the event is having exactly 2 girls. So in this case, we have to check the cases or the possibilities with 2 girls, just this one and this one. So if you write them as a set, will be B. Okay, and also we forgot this one also. So it will be a boy, girl, 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 boy, girl, and girl, girl, boy. And we have more than one outcome here, more than one outcome. So it will be compound event. Now four boys. So is there any four boy here? Four boys? No. In this case, our set will be just empty set. So what kind of event is it? It's impossible event. So as you see, it's impossible to get four boys because we have three children. And let's look at this one. Have at least one boy or one girl. Um, so in all cases here, we have at least one boy or one girl. So the set will be all simple space. So F will be equal to S, which is all space. And this is a certain event. And you can understand it from here, it's equal to the sample space, or you can say, you can also think, okay, in this set, if we have three children, at least there will be one boy or one girl. So this is for sure. Now we said the events are corresponding to the events. The events are corresponding to the subset and vice versa. And now let's look at some operations on sets and their correspondence on events. Now, the event of A or U happens. Okay, how can you calculate? How can you find the set corresponding to that event? It's indeed equal to A union B, A ittihad. You know, it makes if A is this set and B is this set, so the A union B is this set. So then, so you can say this A or B. The event A or B corresponds to A union B. And then, if someone is asking you about the event A and B happens, so in this case, you will calculate. I mean, you will find the intersection of these sets. So you can say A and B. So if you want to calculate, if you want to find the set corresponding to A and B event, the event that A and B happens, then it will be A intersection B. Then there's one more definition here. Two events A and B are called disjoint or mutually exclusive if A intersection B is empty set. So it means mutually exclusive means if A happens, B cannot happen. Or if B happens, A cannot happen. So they are excluding each other. So we say they're mutually exclusive. If one happens, the other cannot happen. So let's say not or, it's and, by the way, it's and. And there's one more definition, and this definition is about complement of a set. So if let A be an event, so it means it's a set. The event that A does not happen is denoted by A bar. And A bar is also called the complement of A. So if this is A here, the yellow part is A, then its complement is the outside of A. And this whole thing is the sample space, is the rectangular region, the big region is S, but in here this is A, and the complement of A is just the blue part. So you can say not A is indeed A bar. We denote it this way. Now let's look at this example. Now if we select a ball from an urn containing balls numbered 1 to 12 randomly, we obtain this sample space. So write the corresponding set for each event. So A is equal to getting an A, getting a 9 is just 9 here. So these are the outcomes here when you draw a ball from the urn with 12 balls. numbers from 1 to 12. So B getting an even number, so we find even numbers in the set 2, 4, 6, 8, 10, and 12. Now C is obtaining a multiple of 3. Multiple means mudaf, so it will be 3, 6, 9, 12. And B intersection C will be just the common elements between B and C. So if we look at B and C, we'll get 6 and 12 common elements. Now B union C will give us all the elements in B or C, 2, 3, 4, 6, 8, 9, 10, 12. Okay, this makes the union. And D, if D is 10, 11, 12, E is 2, 3, 4, 5, 6, then what is the intersection E? The intersection the intersection E is just the common elements between D and E, which is empty set because there is no common elements. And the complement, this is complement of B. So these are the elements of S except the elements of B. So we will just find the elements of B. So these are the elements of B. So we take the rest of them, 1. So these are the even numbers, so we will get the odd numbers in 1, 3, 5, 7, 9, 11, and that's it. Now here are the list of the answers. It's well written, so it's readable, more readable. And here one thing is, remember that if two events have no common in common or no elements in common, then we say they're mutually exclusive events, or we just say disjoint events or disjoint sets. Now let's look at this exercise. In a family with 3 children, let A be the event that family has exactly 2 boys, and B the event that family has at least 1 girl. And so according to this, find the following events. Now, if there are 3 children, we know the sample space. The sample space will be boy, 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 and boy, boy, girl. And then, we can write them the rest, so we can use a tree diagram. And there will be 8 possibilities. We know them, 8 outcomes. Now, A be the event, the family has 2 boys. So you can say, okay, it will be 2 boys. It means there will be 2 boys and 1 girl. So in this case, it might be the first two children are boys and the third one girl, or the first one boy, the other girl, the other boy, and then the other one is maybe first one girl, and we have 2 boys after the girl. So B, at least 1 girl. So at least 1 girl. At least 1 girl means there will be maybe boy, boy, girl, and boy, girl, boy, and girl, boy, boy. So these are like 1, but at least 1 girl means 1 girl, 2 girl, or 3 girls. So these are the cases for 1 girl. So these are the cases for 1 girl, 1 girl. And now let's look at the other cases. 1 girl, and now how about 2 girls? So we can have this girl, boy, girl, 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 boy, and boy, girl, girl. So how about 3 girls? So the 3 girl is only option is like 3 G's here, girl, girl, girl. So here, as you see, these are the subsets corresponding to A and B. Now it says A intersection B. What is A intersection B? Let's look at So let's see if there's a common element between them. This one, yes, and this one, yes, and this one, yes. So A intersection B will be just A itself. So BBG, BGB, and GBB. So how about A union B? You look at A union B. It's since this is A here, A is included in B, so A is a subset of B. So when you, if A is a subset of B, then when you make the union, you will get again B. Now, how about A complement of A? So the complement of A means the rest of the possibilities except A. So we'll try to list all the elements that are not in A. So the elements that are not in A. So how about boy, boy, boy? You can do it better if you have the complete list of the sample space here, but I didn't list them, so I will try to do it myself. So one thing we can say here is, since we have 8 elements here, 8, and we have 3 here, 8 minus 3, there will be only 5 elements in the the complement A of A. So BBB, then BBG, so BG, BGG, and I don't want to take those. I want to take the rest here, G, BGG, okay. There's 4, and there's the last one here, GGG. So as you see, A and its complement, they complete each other. I mean, they when you make a union A complement, it will give you the sample space. Now, how about B? The complement of B. So the complement of B is, okay, let's see what it is. So what is B bar? The B is here. So how many elements? 1, 2, 3, 4, 5, 6, 7. 7 elements, but the space is 8. So there's only one thing left. So it's the complement of B is just B, B, B. Because you will check this sample space and you will check the elements in B. The elements that are not in B are making the complement of B. Now let's look at the definition of probability. Probability is a numerical measure for the degree of certainty or uncertainty of the occurring of an event. So occurring means like happening. So there are 3 types of possible probability. One is classical probability. We use it all the time. And the empirical probability, this is also used. And there's a subjective probability. This is since it's kind of subjective, so it's depending on the person, so it's not used much. But we will see all the examples. Now let's start with the classical definition of probability. In classical probability, we use the sample spaces for sure, and we look at the event. So we look at the event inside the sample space, and we try to measure the probability by comparing the event and the sample space. And here we assume all outcomes are equally likely to occur. So it means they have the same chance of occurring. Equally likely means they have the same chance of happening, same probability or a chance of happening. Now, here is the formula for the classical probability of an event. So the probability that A happens, so we generally say the probability that A happens is, okay. So you find the set A, and you find the set, the sample space, and you are looking at the elements in A, the number of elements in A, and divide it by the number of the sample space here, number of sample space. So the number of the elements in number space, in sample space, sorry. Okay, we will see that in now, let's look at the experiment of tossing a coin 3 times. So find the probability of getting 2 heads. Now, the first thing we have to do is, okay, what happens, what are the outcomes if we toss a coin 3 times? So how can you find it? So basically, you can say this is first toss, and second toss, and the third toss, and then here you can say you can do some tree diagram. You might have head, tail, and then for this one, for the second one, we have the same possibilities, and we have the same possibilities for the third one. Now then, you can write the elements in the write all the outcomes in the sample space. So here is the sample space. H H H H T T. Here another one. You can make the list with the tree diagram. So after this, all the branches are, each branch is corresponding to an outcome. And the number of the elements in the sample space is 8, 1, 2, 3, 4, 5, 6, 7, 8. Or you can do it like 2 to the third power, which is 8. Also, you can do it this way. Remember the counting rule. And then we want to find getting 2 heads. Getting 2 heads is our event. So event is, so let's not say sample space, but let's say the set of the event getting 2 heads. What is it? So which ones are getting 2 heads here? This one, and this one, and this one. So we write them here. So we list them. So this is A, and then we have 3 elements. And now we can write the probability of getting 2 heads. It is 3 over 8. 3 over 8. Now let's look at this exercise. Assume 2 dice are rolled. Find the following probabilities. Now the first one is the probability that the sum of the numbers on the dice is equal to 9. So let's think of 2 dices, and let's say the first dice shows X and the other dice shows Y. And the outcomes here for, okay, X, Y ordered pair shows the outcome. And the list of the outcomes here is like 1, 1, 1, 2, and you can list them. And we already did before. So this will be like 36 outcomes here in total. And we want to figure out what's the probability that the sum of X plus Y equal to 9. So we have to count the ordered pairs satisfying X plus Y equal to 9. Divide by all xy's, the number of all xy's. And we know this one is 36. So we have 36 outcomes. This one is 36. So for this one, we have to list all the xy satisfying this property. And this property is, we can start from 3, 6, because we cannot say 2, 7, because 7 is not on the die. And then 3, 6, 4, 5, and 5, 4, 6, 3. So there will be just 4 of them. So 4. So it will be just 4 out of 36. So it will be just 1 over 9. Now let's look at here. Uh, Probability. So we want to find the probability that the sum of the two faces on the dice is greater than 8. So if you write it in terms of x and y, you want the probability that x plus y is bigger than 8. So we have to find all the ordered pairs satisfying x plus y bigger than 8, and then divide it by the total number of xy's. So this is for sure 36. And if x plus y equal to, bigger than 8, it means x plus y is equal to 9, or x plus y equal to 10, or x plus y equal to 11, or x plus y equal to 12. Okay, this is the best we can have because it can be only achieved by 6. Okay, the ordered pairs here satisfying x plus y equal to 9 is, we will start with 3 and 6, and then 4, 5, 5, 4, 6, 3. And for this one, we will start from 4, 6, because otherwise we have 7, so 7 is not on the die. So 4, 5, 5, 6, 4. And for this one, we have 5, 6, and 6, 5. And here for this one, we have just 6, 6. So when we count all of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there will be just 10 outcomes here. So we have to write 10 in the numerator. So the probability is found 10 over 36. Now let's look at the other probability. The probability that the absolute value of the difference of the two numbers on the dice is equal to 2. So here it's asking the absolute value of the difference between two dice is equal to 2. So we have to do the same thing. We have to list all the xy's such that the absolute value of x minus y equal to 2, and then divide by all number of all xy's, all ordered pairs. So this is 36 for sure. And let's list the xy's whose difference is 2 or minus 2. So we can say here 1, 3. If x is 1, the x is 2, it might be 2, 4. If x is 3, then it might be 1, and it might be 5. And here 4, 2, and it might be 2, 4, and then 5, 3. Sorry, this is 3, 5. Okay, 5, 3. Since they're ordered pairs, okay, 3, 5, 5, 3, they're different. Okay, we'll count them. And 2, 4, 4, 2, and 6, 4, and 4, 6. So it makes 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has to be 9 over 36. So in the last question, it's asking the probability that the product of the numbers on the dice is equal to 9. So we have to find the number of xy such that x times y is equal to 9 divided by all xy's. We know this is 36, so we have to find the xy such that xy is equal to 9. So the only possible thing is like what are the possibilities? 9, 1, 1, 9, 3, 3, but this 9 cannot be on a die, so it will be 3, 3. So just one, there's one possible. There's one ordered pair set to find it, so the answer will be 1 over 36. Now let's talk about the empirical probability. In the empirical probability, an experiment is done, and the outcomes of the experiment is written, and it's done n times, let's say, and in n times we have the event A. So then what's the probability of A, or the likelihood of A? So it's how many times it's repeated in the experiment divided by the total number of experiments. So we can find the probability this way in empirical probability. So it's just almost same as the classical probability. So it will be just the total frequency here and the frequency of A. So the repetition of A, the number of repetitions in A of A divided by the total frequency. Now let's look at this example here. 45 students took statistic final exam. 3 of them got A plus, 5 got A, 8 B plus, 11 B, 9 got C plus, 6 got C, and 2 got D, and 1 student got F. If one student is randomly selected, find the probability that the student is a C plus student, and find the probability that the student is a D student. Now, if you write them in a frequency table, so A plus, its frequency, we can say how many students got it. It's 5, and then B A is sorry, this is 3, this is 5, and then we have B plus 11, 8, and then we have B 11, C plus 9, C 6, D 2, and one student got 1. F, sorry. And then in total we have 45 students, because it says here 45 students took the exam. And according to this, what's the probability that a student, when we choose a student, then what's the probability that he is a C plus student? Now, we remember it, so it's the number of C pluses, or the frequency of C plus, divided by the total. So this will be just C plus has only 9. It will be 9 over 45, which is 1 over 5. So the probability that this student is plus student is 1 over 5. And you can do the same thing here. The probability of D is the number of the students who got D divided by the total, and this makes, okay, D is 2, just 2 over 45. Let's look at this exercise. Students of the prep year can be classified according to their track of study as follows: 457 in science track, 296 in health track, 568 in engineering track, and 58 students in community track. If one student is selected randomly, find the following probabilities. Okay, now you can stop the video and try to do it yourself, and you can check your answer with mine. Now, first, it's better to write them as a frequency table, because this way it will be better to see, easier to see. Science is 457, and in health track it's 296, and in engineering track we have 568, and the community track it will be 58. Now in total, the total number of students is 1,179. Now according to this information here, let's find the probabilities. The probability that he is studying in science track is the number of the science students divided by the number of the total. So it will be 457 divided by 1,179. And in the same way, we can say the probability that he is studying in the health track is 296 divided by 1,179. Now, what is the probability that this student is not studying in community track? Now, there are two ways of solving it. So I want to use complement here. So we want to find the probability that he is not in community track. So we know it's 1 minus the probability of community. So this is the complement rule here. And if you see a not here, so you can use it like the P of the probability that he is not in community track is 1 minus the P of community, the probability that he is in community. So 1 minus, what's the probability of community? This is 58 over the total, so it has to be 58 over 1,179. You can do this calculation by a calculator. He is studying in the sciences or engineering track. So this is the question here: science or engineering track. Now for this one, you have to count the number of the students in science track and the engineering track, because it says science or engineer. So you have to find the number of the students that are who are in science or engineering. So it has to be 457 plus 568 divided by 1,179. Now, what's the probability that the student is studying in the sciences and health track? So, science and health track. So, is there any student in the science and health? So they don't have any common. There's no student with science and health at the same time. So the number of students in science and health is 0. So 0 divided by 1,179, which is 0. So yeah, the probability that a student is in both science and health is 0. The probability that the student is not studying in community or science tracks. So in this case, it has to be, okay, what does this mean? Not studying in community or science track. So it has to be kind of not in community and not science. So in this case, you have to calculate all the number of the students that are not in community and that are not in science. So community is 58, and that's okay. How can you find them? Okay, basically, not community is not 58. So it has to be not community and not science. So the best thing we can do is we can take the sum, subtract community, and subtract size. So divided by the total. So this will give you the probability that he is not studying in community or science tracks. Now let's talk about another type of probability. This is subjective probability. Subjective probability is based on a person or group experience or guess that an event would occur. So, for example, weather forecasting and predicting the outcomes of sporting events. So they are generally personal. Personal. It requires some personal experience, not depending on a concrete data, but it's depending on the person experience or a group experience. And the guess or estimation need an experience and knowledge regarding the event, and the probability is subjective to a specific event, and it's kind of personal. So depending on the personal experience. Now let's talk about the classical probability rules. There are four basic rules. Always keep in mind, the first one is always keep in mind that the probability of an event is always between 1 and 0. So if probability cannot be 2, probability cannot be 3, probability cannot be negative number because of this. Because of this, the probability always between 0 and 1. Now, the second rule is if an event cannot occur, then the probability is 0. So we say this is impossible, probability is 0, it cannot occur. And the third event, an event E is certain to occur, so it will happen in any case. So we say the probability of this event is equal to 1. And the other one is the sum of the probabilities of all outcomes in a sample space is 1. So it means the probability of all events, all the disjoint events, or all the outcomes of the probabilities of all outcomes in a sample space, their sum is equal to 1. So it means one of the outcome will happen for sure. Let's do this activity. When a single die is rolled, find the probability that we get a number less than 7. So find the probability that of the event A, which is getting a number less than 7. So what's the probability of getting 7? So if you write all the outcomes, the sample space will be 1, 2, 3, 4, 5, 6 because we are rolling a die here. You know, we have a die, we roll it, and then we have, since there are 6 spaces, then these are the outcomes. But let's list all the elements, all the outcomes of the event getting a number less than 7. So, you know, in finding the probability, we write the set notation for an event. We list all the outcomes related to the event and we count them. This is A, which is 6, because it's getting number less than 7. 1, 2, 3, 4, 5, 6. So it's same as the sample. So we use the classical probability definition, which is a number of outcomes in A, so which makes 6, and the number of outcomes in the sample space at 6, so it's equal to 1. So we say this is a certain event. So this is, you know, also you can say, okay, a number less than 7 definitely will get something less than 7, so it's the probability. So activity 2. When a single die is rolled, find the probability that we get a number greater than 6. So is it possible to get a number greater than 6 when we roll a die? It's not possible. So we can show it by using classical probability definition. So here is the outcomes, the sample space for rolling a die, and B is the event that we get a number greater than 6. So this is not possible, or we say it's empty set. So then if you use the classical probability definition, so it has to be 0, the number of the outcomes in B, which is 0, and all the total outcomes 6, so it will be 0. So you say this is an impossible event. Now the probability of the complementary events. Now here the complement of any event A is notated by a bar. So what can I say? Here is a bar. When you see a bar, it means the complement of A. Now it consists all the outcomes in the sample space that are not included in A. So this is, you can say, as an event, if A is an event, A bar is not A. So we can write it this way, or we can say also this is the event that A does not happen. All of them, this one, this notation, or complement of A, or not A, or the event that A does not happen, they come to the same thing. And the relation between BA bar, you can also write this one, B not A plus BA, the probability of A is equal to 1. Also, you can say the probability of not A is equal to 1 minus the probability of A. So these, they're same. Now here is the set notation for it. If this is A, low part, and the rest of it, outside of A, sample space is called the complement of A, or A bar. Now let's look at this example. Suppose 66% of people living in Saudi Arabia are aged under 30 years old. If one person is randomly selected, what is the probability that he is 30 years old or above? So we can say this is kind of an empirical data. It means 66% of the people, if they are they are less than 30 years old. When you take a person, then it's when you choose a person, the probability that he is under 30, okay, less than 30 years old, is 66%. You can say that. So this here you can say by using this information, you can say the probability that a person is less than 30 in Saudi Arabia is equal to 66%. So which means it's 0.66. Now it says if one person is randomly selected, what's the probability that he is 30 years old or above? If a person is, we say, what's the probability the person is bigger than or equal to 30? So this is indeed just, if it is A, this is just not A, so it's complement. So we say it's 1 minus the probability of A, which is 0.666. That will give you 0.34. The probability of complementary events. Okay, we continue. Now let's look at the example here. In an experiment of rolling a single die, suppose the event A is getting an even number. What is the complement of A? So if A is getting number, and what is not A? So it's A bar is not A. So the complement here, so it's equal to getting an even number if this is A. So not getting an even number is A bar, not getting an even number. So this means getting an odd number. Odd number. So it will be P of A bar is equal to 1 minus. Okay, now it's not asking the probability. Now, what is the complement of A? So it's asking, so A is just even numbers 2, 4, 6. So remember that we are rolling a die, so we have the numbers 1 to 6. And A bar, the complement of A, are the elements of the sample space, the outcomes of the sample space that are not in A. It will be just the rest of the outcomes, 1, 3, 5. Or you can say the odd numbers. What's the probability of two events? So the probability of A is 3 over 6. And also you can calculate what's the probability of the complement. It's 3 elements here. The probability of A bar is equal to 3 over 6 again. So when you look at them, when you add them, they will be equal to 1. Now let's look at the worksheet problems. So a football player thinks that his team's probability of winning its game is about 0.35. This statement is an example of which kind of probability. Here, the important point here is the football player thinks that the probability of winning the next game is 0.85. So this probability is coming from the football player's thinking, or this is his idea, or it's coming from his experience, personal experience, or group experience. So for this reason, it's just a subjective probability. So how many outcomes are there in the sample space if a coin is tossed 3 times? Now, one way to calculate is, there are one way and the second way. One way is to list all the sample space. The first method, I will say, just to make the list. So we can say first toss, second toss, and the third toss. So you can say in the first toss you have H, head or tail. In the second one you have the head or tail, head or tail. And in the third one you have this head or tail, head or tail. You can say head or tail here also. We have head or tail. So if you write all of them in the sample space here, all the outcomes, you write all branches here, H, 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 and H, H, T, H, H, T, and then T, T, H, and H, H, T, H, and H, T, T. And then THH and THT and TTH, TTT. Now it gives all the sample space, all these branches. So we have 1, 2, 3, 4, 5, 6, 7, 8. So it will be 8. Or the second method here is this one. Flipping coin one time is, you can say, the one trial, one toss. One toss is making 2 outcomes here. It will be just 2, the head or tail. Now, according to the formula here, we learned before, if you have independent events, tosses, and if you do it 3 times, 3 tosses, then the outcomes will be the outcome number for one toss to the 3rd power. So it's like one trial is k outcomes, if you remember it, Then we have for the n tosses, we have 2 k to the n power. So we have 8 also here. It's 8. Okay, we already found the answer of this question in the previous one, because it says if a coin is tossed 3 times, the sample space is, okay, you can use the same thing here, the first toss, second toss, and the third toss. You can use a tree diagram to find, all the uh, outcomes here. You can do the rest. I mean, we already did it. And if you count 1, 2, 3, 4, 5, 6, 7, 8, and this is H, 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 T, H, T, H, and nothing is repeated. So this is the answer. It's coming from here, this tree diagram. If the set of outcomes in a sample space that are not included in the outcomes of an event is what? So we are talking about the sample space here. There's E, but we are talking about the elements of S that are not in E. Not in E. So it means these are the elements of not E. Not E means the complement of E. So it will be a complement event. So this will be the complement of E. The box contains 11 apples, 14 oranges, and 5 bananas. If one piece is randomly drawn from the box, find the probability of getting an apple. Now, getting an apple is, okay, if you use the classical rule of probability is rule, the probability of apple, okay, choosing an apple, let's say choosing an apple is equal to the number of ways of choosing apples, choosing apples divided by the number of ways of choosing all fruits. Now this, in how many ways we can choose an apple, because we have 11 apples, so it will be 11. So in total, how many fruits are there? This is 30, so it will be 30. So it will be 11 over 30. So you can basically say like the number of apples divided by the number of all fruits. But the idea is the ways here. So the number of the ways. And this is equal to the number of apples, of course. And if the probability that a new drug will be successful is 0.15, find the probability that it will be, okay, by the way, this is equal to C. If the probability of a new drug will be successful is 0.15, and find the probability that it will not be successful. If this is A, drug will be successful, this is the event, and then it will not be successful is not E, or A bar. Now it's saying the probability that A will happen is 0.15. It's asking what's the probability that it will not happen. So the probability that it will not happen, not A will happen, so it's 1 minus the probability of A. By using the complement, you can say 1 minus 0.15, which gives you 0.85. It will be B. Now assume, okay, I will change this question, like assume a die is rolled 1 time, then if A is the event that let's say event of getting 2 or 4, find the complement event of A. So here you have to do what? You have to list all the elements of A. Getting 2 or 4 means 2, 4. So getting the complement complement of A means A bar or not A. Say, so what is this equal to? It's all the elements of S except the elements of A. So it will be 1, 3, 5, and 6. So it will be just C. So, okay. And Fahd chooses a number uh, from the list 99, 107, 211, 478, and 481. Find the probability that the number he chooses is greater than 400. So, what's the probability that he chooses a number bigger than 400? So we have to say this is the number of the numbers bigger than 400 divided by the number of the total number, total of numbers, which is 5. So we have 5 numbers here, and we have 2 numbers bigger than 400. So it will be 2 over 5. So which is 0.4. This numbers bigger than 400 is these 2 numbers. So we say 2. In a sample of 50 people, 20 had type O blood and 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Now this is given in this table here, the frequency table, the blood types. Now the question is, find the probability when we choose a person. Find the probability that a person has 0 or O blood type. So this has to be equal to the number of O bloods and divided by the total. So this is 21 divided by the total is 50. Now let's look at the second one. A or type B. So a person has type A or B. So in this case, you have to look at the number of A's and number of B's. So you have to add them because it says A or B. So you will count A's, we will count B's, and then divide by the number of total. So here A and B, nothing in common, so we add them. So 22, 5, 27 divided by 50. Now a person has neither type A nor type 0. I mean type O. So in this case, let's look at here. This one here. Okay, neither type A nor 0. So what does this mean? This means we are talking about the number of people that are not A and nor not O. So it means we are talking about B's and AB's. And since they're not common, we just add the numbers here of B's and A's. AB's, sorry, this is 5 plus 2, it's 7, divided by the total number is 50. Now, a person does not have type AB blood. Now, I want to do with the complement here, what is the probability that it's not AB? So you can directly say this is 1 minus the probability of AB. So 1 minus, what is the probability of AB? The number of ABs divided by the total. So it has to be 48 over 50. Now, if two dice are rolled one time, find the probability of getting these results here. These are the results. And this is just a table of the outcomes of all possible outcomes of rolling two dices. Now it means like when you take one, it means you got this one here, the one it's here, and the first one, the first dice, and the second dice here means here we got one. Anyway, so I will say, okay, now in general, I will write our outcomes as x and y. So we have, assume you rolled two dices and we got x here in the first die, and assume we got the second one as y. Now, so it's so the x can take the values 1, 2, 3, then it will be 1. So okay, if you list 1, 2, 1, 3, and it goes like 6, 6. So how many in total? In total 36. So it's here. So they are listed in here. Now, what's the probability that the sum of these x and y is equal to 6? So you can write this one like bx plus y is equal to 6, which is the number of xy's ordered pairs such that uh, x plus y is equal to 6 divided by total. So total number of xy's. So I can say here, okay, let's try to find them. We want to find the xy's such that x plus y is equal to 6. So for example, 5, 1 makes 6, 4, 2 makes 6, 3, 3 makes 6, 2, 4, 5, 1. So in total, we have 5 elements here. 5 elements, and in total, the outcomes are 36. So it will be 5 over 36. And the double here means we want to find x equal to y. Okay, so what is x? X is the outcome of the first dice, and the second one is y is the second one. So this will be all the number of x, y's, the order pairs, such that x is equal to y divided by the total. So when we look at here, x and y's, 1, 1, 1. Okay, let's raise this one. 1, 1, 2, 2, 3, 3. Okay, 4, 4, 5, 5, 6, 6. So this will be just 6 numbers here. So we say 6 divided by 36. Now this is a sum of 7. Now so we want to find all what's the probability that their sum is equal to 7, or their sum is equal to 11. So we have to calculate the number of xy's such that x plus y equal to 7, or x plus y equal to 11 divided by total. So which makes okay, let's count them. Let's count them. What makes 7? Okay, 2 plus 5 makes 7, and 4, 6, 1, 7. So these are making the 7 here, 7. And 1, 2, 3, 4, 5, 6. Okay, we have 6 here. And what about the 11? What makes 11? So it makes 6, 5. 5, 6 makes 11. These are making 11. So 2, we have 2 more divided by the total. So it will be 8 over 36. Now is sum less than or equal to 4? Okay, I will erase this part now. number less than a sum less than or equal to 4. So it means x plus y is less than 4. So we have to check the all xy's, the number of all xy's. This, this symbol is the number of, so I'm using this for number of xy's such that x plus y is less than 4 divided by the total. So let's count them. This x plus y is equal to is less than 4, so it makes 1 1 1 2 1 3. No, we cannot take 1 3 because it makes 4, and 2 1, and okay, so less than or equal to 4, so it will be equal to 4. So we can take this 1 1 3 2 2 and 1 3. So how many here? It's 6. So it will be 6 ordered pairs divided by 36. So this will be, okay, if you simplify it, 1 over 6. So this will be the answer for this probability. Goal to find the probability of getting 6. Okay, the sample space is 1 2 3 4 5 6. So we have in total 6 outcomes. Getting the number 6 is like 1 over 6, because one of the numbers is 6 and we have 6 outcomes. It will be 1 over 6. Getting an odd number, so it means you have you can get here the odd numbers. You can get 1, 3, and 5, so it makes 3 numbers here. And in total we have 6 numbers, so it will be 3 over 6. A number greater than 3, so greater than 3 will give you 4, 5, and 6. We have still 3 numbers. We say it's 3 over 6. And greater number than or 3 or odd number. So okay, this is important. Okay, this is an important one, so I want to list them separately. So it says a number greater than 3 is it can be 4, 5, 6, but it's an odd number. Odd number can be here 1, 3, and 5. So since this is or, I'm taking the union of them. So I'm taking the union of them. So the event will be equal to 1. So it means getting 1, 3, 4, 5, and 6. So when you check the union, you don't repeat the 5s, by the way. So how many numbers in total? You got 5 numbers. So 5 numbers you got. And what's the probability? The probability is 5 over 6. So because this 5 is coming from this part here, and this is, we know it's the total here. It's coming from the sample space. Okay, that was a long and that was long video, so I had a hard time to prepare it. It could have been done better, but anyway, I didn't have time.